Okay, so we continue on the perturbation theory. Today is about okay. So let me in the previous lecture, okay, we deal with the Hamiltonian operator, which is okay, right, in this way, which is, well, you can say that actually this is time independent Hamiltonian. But actually, the variable t actually sits inside these variables p and x right here. So in this situation, we going to deal with the Hamiltonian, which is actually the potential function probably depends on time. That is the one that we are going to look at. Okay, so let's so normally we know that actually there are two cases in this situation. The case that actually you look at the bound state, right, and unbound, bounded, right here. So suppose that we look at the first case, that bounded state with n level system. Okay, so you know what I mean by n level system, right? Okay, so then in this situation, the Schrödinger equation I could put in this way. Oh, no, sorry. Oh, okay. Let's put the L, where the L landing from to N. Okay, and this is independent Hamiltonian. Okay, I put this as H0 there, and which of course that you can turn this to the Dirac bracket, and you have to have this relation, right? Okay, or if you don't like Dirac bracket, you might this is not really a right way to put things, but because a right way to put things, let's suppose this is the functional space, right? And then you say that, okay, this is the way you will put there. And if you don't like this direct bracket, so you can, of course, that right here. Oh no, it should that is yeah, I think it's okay to put in this way. Yeah. All right. Okay. So we know that a general solution, I mean a complete solution of this system is just a superposition of possible solution that you could have, right? So suppose that, so here, right here, this is does not depend on time, right? And this is the constant, right here. Okay, and then so the normalization condition require this summation right here. And now, and you know that, well, you can study the evolution of this wave function to the unitary operator, right? That we are not going to talk about that yet. But anyway, so what we are going to do next is to replace this time independent Hamiltonian with this one, right? With the time dependent Hamiltonian, right? So the wave function psi out. Where is it? Okay. So yeah, okay, psi out. Can be expressed as linear combination of this one. However, this is the wave function needed to be modified, right? Because you cannot, because this is the solution for time independent Hamiltonian, right? But you cannot use this use those solution right away with a new Hamiltonian that you replace the H dot there. Then that is the reason we need a modification, and only one place you can do is by replacing. Can you get? Now we have this as a solution for this. And then, so if we want to modify this solution to make it satisfy a new operator, which is actually now depends on time, which part of that solution that we could do the modification? Can you guess? Can you guess which part of this solution that we can modify? Which part? Exponential part. Interesting. How to do that? Expand it. Okay. So if you want to expand it, you need to put a parameter, right? But here you get you have the energy, and so I don't know, that can be I don't know that it makes sense to treat this energy level as a parameter that you can expand. And what you expect when after you do expansion? What do you expect to get? Yes, but you still get this. You still get nothing. You see what I mean? Even you do the expansion of this exponential, right? But you still get exactly the same. This wave function, nothing changed at all. Because after, well, if you put things back to this form, you still get the exponential, nothing really changed. So the best way, the best place, actually this CL, this is constant, right? We just replace this with that actually depends on time. And you need to find a condition for this C that actually satisfies this new Hamiltonian. That is the thing. Okay, so now we have zero or no one, n here. So what you need is this one to be mean, right? That's what we're going to do next. So in doing so, yep. Oh, I might. Oh yes, it should be maybe around. Yeah. Okay. Sorry about that. We consider, okay, this equation. Now you can split okay, you can split your Hamiltonian into two parts. The first one is that actually you can solve exactly right here on this board, and The second part is what we added on. No, actually, I should put palm here, right? Like we did in the previous lecture. Then now we're going to have this kind of equation. You put everything yeah. And so okay, and so what you're going to get is what? So then you move the whole bit here into the bracket. Then what we go into right. You have CLT S0 here plus CLG it's not difficult, but it's a bit lengthy. So I just need to put a minus sign. Sorry about this. Okay. Is that all? I think yes. Okay. And so it is not difficult to see now that this thing and this atom is actually the same. Can you see? Because after you apply the showing this operator, you get E, right? And then this going to have you're going to have E, and then RH bar going to kill each other and so on, and then yeah, you're just crossing it away. So what you left is that. Okay, so you have this one. So the next step, I'm going to apply orthogonality condition by multiply phi alpha from the left hand side. So what you have on this bit is CL, and then you have this okay, so I think it should be there. And from this side, you have okay. And so this is going to give you this delta function, and then with this summation, it's going to select only one L, which is L equal to L prime, right? So this means that so you're going to get C dot L prime E L prime T. So sorry, let me put here up there to here. Okay. Then okay. And from this side, so you can split it into two terms. The term that actually L equal L prime, and another one is L not equal to L prime. Then, so for the L equal to L prime, you will get this, right? And plus all the rest that actually L not equal to L prime, right? Yeah, right. So it means that, so now you can solve for C dot, right? So your C dot, I put maybe F T. It doesn't matter you're going to put F or L, is it's just a dummy index. Okay, you have this. It means that, so we have now n copy of this equation, right? To solve C dot, right? I can, so to make you see the whole structure, we can explain things in terms of the matrix. And so you will see, so this is going to be C1, C2, C3, right? And then you get Cn here on this side, right? Because F the F is running from 1 to n, or maybe well, we just throw away the 0, it doesn't matter. Okay, it depends on the system actually, and you get H11, H12, T, H13, omega 13 is a bit huge matrix, but I think it is not difficult to write down. One, 2, and this is 2, 2, 2, 3. Zero. Okay, and I'll put it one more okay, and so you have another column which is here. Okay, so right, so now from this equation you can turn it into the matrix form like that, where I need to clarify my notation a little bit. So H okay, it's this one, okay. Okay. So we need to check whether this equation making sense or not. So check if this part 0, it means that your Hamiltonian, this one, will become just the standard that we know, which is we know that actually CL is nothing but constant, right? So if we take away this part, sorry, you have to put the pound there. So if you check and then you find out that actually you get everything will be 0. because you see that all the elements here in this matrix actually you have all the echelon. So it means that equal to 0, it means that CL constant. Okay, it's kind of, so it gets this kind of, when you consider the in the case that this part go away, you recover the previous card, the previous case, right? That kind of okay. Sorry. Oh. Okay. So if we treat now, if we treat this term in a very weak effect, right? So because we want to do like a perturbation right here, then we consider that if this term is very weak, what will happen? Then this CL should slightly change from its initial value, right? Suppose that its initial value is that this one, which is actually CL, right? Like this one, you haven't turned. You can think that actually in this situation, you turn off this bit, right, as the initial condition. But once you turn this on, you need to consider how the dynamics of this variable, that is the thing, right? In when you like slowly turn it on, that's a kind of thing. Then from this. Oh, I haven't defined my omega here, right? Omega, okay, it's EL, EK, right here. Is that H bar, right? I think here. No, no, it should be OH bar, right? Yes. Otherwise, it's, the unit is going to be something else. Okay. So you have this kind of differential equation to solve. So you now set okay, this is initial state. Okay, because I can do this because I put this condition here, slightly change, then it's kind of change a bit, right? That kind of thing. So what we're going to have here is that okay. So what I did, I just put the delta function into this on the right hand side, and with this delta function is going to eat normally use the word eat the summation, right? You can say that actually it is going to take away summation, and then it's going to give you only the case that L equal to I, right? So what you get is that IL plum T and H IL plum. I think I forget to put palm here, right? It should be palm here, right? It should be palm here, right? So basically, you can solve this equation, right, by just doing the integration, right? Okay, in this way. And sub constant, right? Maybe. No, but well, it's not necessary to put that back. You can this. So we can conclude that this is going to be the amplitude, right? Amplitude of sliding perturbation system in the unperturbed state alpha at time t. Okay. let's check whether my equation satisfy this condition or not. Can you see? Is it satisfied? Because if I put t to be 0, then this whole term will vanish, will go away, right? And then I haven't covered this delta function, right? Then it means that I have to add, right? To make sure that once you put this, to make sure that when t equal to 0, we will recover this condition, okay? All right, okay, so let's continue to what time is it now? Just 1 hour. 1 hour left. God. Okay. So up to this point in equation. So now, if not, then we look at perturbation series. Okay. So from this oh, well, please don't confuse the index. I mean this I, and then, but this is the index. So sorry about this. I just noticed that. But well, you can change to something else if you like. Sorry about this. So where are we now? Actually, and so from here, we may write things in this way. Okay. And then what I did is it should be palm here. Sorry. So what I did, I called it, okay. Oh no. Okay. So let's see what we could get. Should be tau sigma KL sigma and H here, sorry, there. KL sigma CL sigma CK, right? CK here. So what I did is that I just put this whole equation into this, then right. All right, so sorry, this should be tau, right? Yes, sorry about this. Should be tau, okay. And then you expand the bracket. Once you expand the bracket, you will get a lot of terms. But let's see what we could, what we get. I think we have this term. I think so. Yeah. Right. Okay. and we continue. Wait. So of course that again I can apply equation called chi at this here again. Okay. So we could proceed further by inserting C. Okay. Right. We can do that, and so well. So you're going to have the infinite, the very huge term. So if you continue doing that, so you're going to have CL right here, and I should see L we're going to have this kind of series. Okay. So this is 0 order, and this is first order, and then this is second order. Okay. And so where okay, the first order here and the second order, I mean, oh sorry, 0 order, this is the first order. Okay. And close that. The second order. This. Okay. And you can put further in the expansion, and we'll get more and more complicated objects, but we are not going to do that. So then we can compute transition plot. Okay. right? Yeah, transition plot. I define this is a transition plot because this is from initial state, right? You this the perturb part is turned off, right? But once you turn on, right? Right, you could see the effect of this thing. Okay, so let's have a look at this example. Because we have compute a lot thing. Let's see how it works with the example. So now you know that actually this is the Hamiltonian for the quantum harmonic oscillator, right? So it has been prepared in the ground state. Okay, at time minus infinity, it means that the usual state has been in the ground state in a very long time, something like that. Okay, and if is perturbed by a weak electric field such that your potential has been modified here. Which is a plot of finding its in first. Oh no! What is the first excited state? At t plus infinity, so this is just a constant. So you know this is the Gaussian like here. It should be constant here time, right? So let's see what we could get. Okay. Oh, sorry. So suppose this is a plot that actually once you turn on the electric field in this way, going to move from the ground state to the first excited state, right? This is the plot that the system will go from the ground state to the first excited state, okay, which is okay. Suppose L equal to 1, right? Not suppose, but actually the 1. L must be 1 because we consider the first excited state, right? L is running from 0 to 1, and then so you can say that this is, you can approximate this C by the first order in this expansion by looking at this first order. Okay, because the zero order give you nothing but the standard, but the system itself in the unperturbed situation, right? So where C1 1 is okay. So we have this. This part is nothing but the H palm, right? This part is nothing but the H palm because now once you turn this part, right, your system has to be composed of this one plus this one, right? Okay, this is in terms of bracket, right? Because you have to sandwich. You know that actually I turn all this thing in the Dirac notation, but actually you can say that this bit is 1, right? V, right, and 0 here, right? And then I turn into the Dirac bracket and right. Okay, using you know that from the standard yeah, right. You know that you can write position operator in terms of the creation and annihilation operators in this way. Let me just replace this thing with just omega here. Okay, then this is actually same omega. So it means that we're going to have here. And so you know that the first explicit state actually comes from this kind of operation. Right. Right. Yeah. Then you get this. So what you get is okay. And then so the left what you need to do next is that you know that actually this whole bit is constant, right? You can pull this out of the integration, and then you do the integration with this exponential and this exponential here. So I'm sorry, because I use the tau here, let me put a sigma there to make sure that this is the different constant. Okay. Okay. And once you finish the whole business, you will get. Okay, and let's take 5 minute break then. Okay. โอ้เรียนจนกระดาษหมดโอเคครับโอเคงั้นขอเบรก5 นาทีเนาะ Okay, let's continue a bit, and then let from this point, so here we get the constant, right? And you can pull out of the integration, and then at the rest you just need to finish the integration, which is actually very simple because it is oh sorry, this should be tau here. This is the Gaussian, right? This is the Gaussian integration. Well, then you can do it very simple, in a very simple way. So it means that so you get here. I'm not going to do the integration for you, but I hope that you can do it yourself. Sigma. Okay. Then so this plot, right, can be expressed M. So this is going to give you a maximum. The pop will get to the maximum at this condition, right? Is it? Okay. So I'm going to give you another example, but it will be the homework. Okay. So this is like you have like a particle in the ground state, and then if you want to make it into the first excited state, you need to add the energy into it, right? And then you see that you see that this is a probability that your particle will be moved from the ground state to the first excited state with this kind of adding or turn on the energy that you put like in this way. Because you can think this is nothing but like you add the energy bunch of like a photon, something like that. Think in that way. Anyway, so but if you can modify your electric field that proportional with this frequency, inverse of this frequency, that you get the highest chance to make your particle move from ground state to the first excited state. That is the thing. Okay. I think I'm going to stop here for today, and so tomorrow we're going to continue further on this topic, and I hope that tomorrow we're going to finish this thing, and next week, are you still here next week?
Next week, and still here until Wednesday.
All right, okay, and then we're going to talk about WKD approximation a bit, and then after that we move to the scattering thing, that kind of thing. Okay, all right, okay, that's all for today, and